Welcome to the presentation of the work Hyperspectral Image Super-Resolution using Convolutional Neural Network in Wavelet Transform. My name is Edgar Pérez Moreno. I am a master's degree student from Instituto Politécnico Nacional, and I will present this poster. The content of the presentation is as follows: a brief introduction to the topic, the methodology of the proposed system, the experiment setup, the experiment results obtained with the proposed system, the conclusion we have reached, and finally, the questions. Hyperspectral images, unlike ordinary RGB images, consist of many bands that store information of the electromagnetic spectrum of some scene, like fields, cities, or crops. The information summed at some intervals of the spectrum wavelengths is stored in the spectral bands, thus forming a hyperspectral 3D cube or hyperspectral image. Due to the above, this type of images have different applications, such as classification or detection of objects. In addition to this, sensors that capture hyperspectral images have been increasing their availability and accessibility in the market, increasing the use and application of hyperspectral images. To make hyperspectral cameras more accessible on various platforms, their size often can be reduced. This directly impacts the spatial resolution of the images obtained, reducing the number of pixels registered and affecting the quality of the applications where these images are used. In the state of the art, you can find various papers related to the super-resolution of hyperspectral images. All these studies can be divided into two groups: a priori and non-a priori information usage. The methods of the first group require another RGB, SAR, or panchromatic image in addition to the hyperspectral image. This implies that additional sensors are required in the scene, which can be expensive or require additional space for the replacement. However, the results of super-resolution that are obtained are usually very competitive because they have more information with which to work. In the second group are the algorithms that only use the hyperspectral image. These methods do not require the use of extra sensors. However, as they don't have so much information, their results are usually lower than the methods of the first group. Another thing to consider is the image spectrum. Many state-of-the-art methods achieve competitive results by increasing the resolution. However, their method distorts the image spectrum, which also affects application with hyperspectral images since its spectrum is the main feature of these images. The problem of super-resolution must be attacked from two fronts: the spatial and the spectral. The spatial resolution must be increased and also conserve or not alter the spectrum of the image too much. This is the root of the problem. The proposed system consists of two sections: the spatial section and the spectral section. In the first section, the super-resolution is carried out. It means a low-resolution hyperspectral image will enter and a high-resolution hyperspectral image will come out. The second section will correct the spectral distortions in the image caused by the first section. Thus, we will finally obtain an image with higher resolution and with the corrected spectrum. In the spatial section, the spatial resolution of the image must be increased. Namely, a low-resolution hyperspectral image can be defined as X belongs to the real, where R, C, and B correspond to the number of rows, columns, and bands contained in the image. The aim of the spatial section is to generate an output image. This image can be denoted as Y, belongs to the real, with double rows and columns, but the same number of bands. The state-of-the-art methods have demonstrated low performance image reconstruction. To solve this problem, the system employs a net extraction approach obtained using the Wavelet transform, as it being proposed by Chavez-Roman and Ponomaryov in reference 1. The purpose of the spatial section is to increase the size of the image, I mean its resolution. The spatial section is described below. First, a low-resolution hyperspectral image enters the system. The discrete Wavelet transform is applied to each one of the band images separately. So, we obtain the HH, HL, LH, and LL subbands. Then, for each processed band image, the Lanczos interpolation is performed in each one of their subbands. Afterward, an edge image is computed using one, where HH, HL, and LH represents the subbands ensued by the discrete Wavelet transform. Then, the original value in the band image is subtracted from the value of the subband LL, obtaining the difference image. Subsequently, the mean values of the edge image in addition to each HH, HL, and LH subbands values are calculated. Then, the average of each one of the previous means, including the corresponding values of the difference image, is computed. Finally, the results numbers are merged with the original band value of the image, and the inverse discrete Wavelet transform is performed to acquire an image 1 with its size doubled. This process is applied to each band of the hyperspectral image, so we obtain a high-resolution band for each low-resolution band, and we get a high-resolution hyperspectral image. This spatial section aims to perform spatial super-resolution on the hyperspectral image using the discrete Wavelet transform and edge extraction to contribute more information for better performance in the reconstruction of edges. The spatial section applies super-resolution to each one of the bands separately without taking into consideration any correlation between them. Therefore, these operations can generate distortions in the spectral domain of the pixels. The spectral section corrects the variations in the spectral components of the image to obtain a high-resolution image with an accurate spectrum. First, the output of the spatial section enters in the spectral section. Namely, a high-resolution hyperspectral image enters in the stage. Then, a tensor of 30 by 30 by 3 is obtained from the image. The tensor enters in a convolutional neural network to correct it. Subsequently, a tensor with the spectrum corrected is obtained. Finally, all tensors are ordered, developing a high-resolution hyperspectral image with a more accurate spectrum. The convolutional neural network combines the spatial and spectral information of the image to result in a correct hyperspectral image. Then, in this scheme, both types of information are exploited in contrast with the spatial stage, where the information of each band is used individually. The architecture of the neural network is described in Table 1. Uses 3 convolutions and has 2 Rayleigh functions. The input of the network is 33 by 33 by 30 tensors. These tensors generate outputs of 21 by 21 by 1. For experimental purposes, we used a database from the University of the Basque Country. This database has 6 hyperspectral images. The resolutions are from 83 by 86 to 1096 by 715, and the band numbers from 100 to 200. The pixels values among the images were far apart, so a normalization process is performed in the 0 to 1 interval. To obtain a major number of images for the experiments, the original images were rotated 90 degrees 180 grades and 270 grades, producing a database of 24 images. The proposed method is compared with other state-of-the-art approaches, those proposed by May et al. And Jia et al. The metrics used for the qualitative evaluation are PSNR, peak signal-to-noise ratio, and SAM, spectral angle mapper. PSNR to evaluate the quality of the spatial resolution, and SAM for spectral evaluation. PSNR is calculated using equation 1, where MSE is the mean squared error and max is the maximum value of the images, namely 1. SAM is employed using equation 2, where X represents the correct image and Y represents the ideal image. Each one of the images has a PSNR value, and each vector of the pixels has a SAM value. So, to obtain a final PSNR and SAM value for the image, the mean of the PSNR value of each one and the mean of the SAM value of each vector are calculated. This slide exposes the error images for Pavia University in Band 20, result from the proposed method and the other methods used for comparison. It can be observed that the main problem of the super-resolution process lies in the reconstruction of edges and fine details. The images present a large number of errors in the areas with a high degree of edges. However, error image of our method present less details than the comparison methods. Our method better reconstructs the areas with more texture and the edges of the images. The next slide presents the error of images for Pavia City in Band 20. It can be noticed that the error image of the proposed method have a better reconstruction of these zones in comparison with the other methods. The results shown in Table 2 correspond to the proposed method and the comparison methods of May and Jia. It can be observed that the PSNR values obtained by the proposed system surpass the similar results given by the comparison methods. This means that the spatial reconstruction performed by the proposed system is better. This can be seen in the error images too, where visual subjective perception shows a better representation of edges and fine details and lower contamination by noise. These results are largely due to the spatial section of the system. The edge extraction that is performed in this section allows to provide more information to the system for a better reconstruction of the image. The SAM values ensued by the proposed system are higher than those resulting from May et al., which means a superior spectral correction by the proposed method. Nevertheless, these results are still lower than those ensued by Jia et al. This disadvantage can be explained by the limitation of the CNN architecture, that is like the one used by May et al. Consequently, the ensured quality results of the proposed system are analogous to their method. The proposed system appears to demonstrate the best results in the spatial domain in comparison with the state-of-the-art methods. It allows a better restoration of the areas with edges and fine details. This enhancement is obtained due to the spatial section implemented in the proposed system, which takes advantage of the edges extraction and wavelet transform to contribute more information in the image reconstruction. The spectral section of the design framework demonstrates competitive performance, resulting in higher SAM values than the method proposed by May et al., but slightly lower than those obtained with the method of Jia et al. This disadvantage can be explained by the limitation of the CNN architecture. Nonetheless, employing more competitive CNN architecture, we suppose to achieve an enhancement in the correction of the spectral variations. The proposed framework combines better spatial super-resolution images provided by an edge extraction stage and wavelet transform with the spectral correction of images provided by a CNN. The developed system addresses to quality in the spatial and spectral domain of hyperspectral images, producing images with corrected spectral properties and higher resolution. For further questions, please write them on the platform. I will answer them. Thank you very much for your attention.